Okay, so I'm going to finish drawing the poles for the plant here. Okay, and then now I have my 0, which I'll draw in blue here, and it's at some unknown location here, right? So I'll call it minus z, right? Because I've added a term at s over z plus 1, so it has a 0 at minus z. And what I want to do is I want to put this point here, okay, which is the minimum, the point that meets the minimum specification. So this is at s equals minus 1.8 plus or minus, actually in this particular case it has to be plus pi times j. Okay, so I want this point to be on the root locus. And so I've got to choose minus z so that that point is on the root locus. So what I'm going to do is I'm going to draw these vectors like this. Okay, and remember the idea is that there is this angle criterion, and so I'll draw these angles. I'm going to call this theta from the first pole, and this is theta from the second pole, and this is the angle from the 0, theta 0. Okay, so in order for this point to be on the root locus, it must be theta z minus theta p1 plus theta p2 is equal to minus 180 degrees, okay? So this is the angle requirement for the root locus. And we can calculate theta p1 and theta p2. Theta p1 is equal to arctangent of pi over 2 minus 1.8. Okay, right, so it's the imaginary part here is pi, right? And the real part here, I guess that's actually theta p2 that I just calculated. Sorry, theta p2. So the real part is 2 minus 1.8. And so when I do that calculation, I get 86.4 degrees. And theta p1 is going to be equal to 90 degrees plus arctangent of 1.8 over pi. Okay, so again I used the triangle here, so it's got length here of pi, and the length along here is 1.8. And so when I do that calculation, I get 119.8 degrees. Okay, so theta z is the only unknown, right? I can choose this 0 position. If I move it way into the left half plane, I don't get very much additional phase. If I start moving it in closer and closer, this angle will get bigger and bigger, okay? So I want to find out how large that angle has to be. So I start with this equation here, and I can write theta z is equal to minus 180 plus 86.4 degrees plus 119.8 degrees. And when I add all this in there, I get 26.2 degrees, okay? So I'm going to place the 0 to add 26.2 degrees of phase. And this is an important concept because later on when I talk about a phase lead compensator, the phase lead compensator is going to add a certain amount of phase. We call that phase lead because normally we talk about the phase being the lag, meaning the phase lag is sort of negative phase and phase lead is positive phase. So I'm adding a little bit of phase here with my controller. And so to find where the 0 is, I can write that tangent of theta z is equal to pi over z minus 1.8. Okay, so that's z to minus 1.8 is the length of the side of this triangle on the real axis, whereas pi is the length of the triangle on this side. And so I can solve for z. So I get z is equal to 1.8 plus pi over the tangent 26.2 degrees. And so I get 8.18. So I'm going to place the 0 at 8.18. Okay, so that's the first part of the answer to this problem. Now, the second question is then how much, so if we go back and look at the controller, right, there's two parameters. I've picked z, okay, so I determined how much additional phase I needed, and so I picked the zero to do that. Now I have to calculate how much gain k I'm going to need. Okay, so I can do that from the root locus. So, so we'll find the gain of the PD controller. And we're going to use the magnitude condition of the root locus. Okay, so now I have a pole here at 0, and a pole here at -2, and I have a 0 way out here at -8.18. And I want to put the, this is my desired position, SD, and I'll say S desired is -1.8 plus j pi, okay? And I'm going to draw, again, I'm going to draw my little vectors here. I have this one, and this one, and this one, and I'm going to call this one L, and I'm going to call this M1, and this is M2. And so we have, it's not so obvious here, I'll write M2, okay? So the magnitude condition of the root locus says that F evaluated at SD magnitude is going to be equal to 1 over k. And, well, F evaluated at SD, magnitude here, is found by, it's the magnitude of this vector, which is from the 0, from the numerator. And on the bottom, I have M1 times M2. Okay? In other words, I could write that K is going to be equal to M1 times M2 over L. So I have to calculate the lengths of all those vectors. Unfortunately, those are easy to calculate. So this L is square root of this length on the side here, which is 8.18 minus 1.8. And I'm going to square that. And I'm going to add the length of the other side. So the length of the other side is this length here. It's pi. When I do that calculation, I get 7.1 here. And M1, similar kind of calculation. I'm going to have 2 minus 1.8 squared plus pi squared. And so I get 3.15. And the third vector has length square root of 1.8 squared plus pi squared. Sorry, it's having trouble refreshing somehow. Equals 3.62. And so I put all those things together, and I find that k is equal to 3.62 times 3.15 divided by 7.1 is equal to 1.6. Okay, and so now I can completely specify my PD controller. GC of S is going to be 1.6 times S over 8.18 plus 1. Okay. So now this is a PD controller that will meet both of the specifications. And so I can just very quickly now draw what the root locus will look like for this thing. So here's what it'll look like. I've still got the same pole and 0 locations. Minus 8.18 here. So the root locus is on the real axis here between the two poles, and it's over here, okay? And so what happens now is that these guys come together. This is -2, this is 0. And I'll go ahead and label this point here that's at, it's like, hopefully this is about in the right place, right? So this point is minus 1.8 plus pi times j. So what happens is now the, sorry, changing the pen color. So now what happens is these guys come together and they will be bending over to the side like this, okay? and it will be exactly at this desired location. So this one is the complex conjugate pair, minus 1.8 minus pi times j. And the gain required to reach this is k equals 1.6. And so you could do this using the RL tool in MATLAB. Or there's another command that's rlocus. It will allow you to sketch the root locus so you can sort of mouse along and find the gain that's required to place the pole at a particular location. But it won't tell you where the 0 should be, so it's helpful to know how to calculate where that 0 should go. Okay. Now I'm almost running out of time, but I want to talk a little bit about why we would use a lead compensator instead of a PD controller. So first problem with the PD controller, it's not realizable. Because it has no poles. Has 1, 0. Okay, so the numerator has order 1, and there's the denominator is order 0. So, like if we write a PD controller, we'd write GC of S is equal to K times S over Z plus 1. This is PD. Okay. There's also what's called a lead, phase lead controller. And it looks like this, GC of S equals K times S over Z plus 1 divided by S over P plus 1, okay? So it has an additional pole. So it has a 0 at S equals minus Z and a pole at S equals minus P. And one way we can think about the phase lead controller, so first of all, it is realizable. This additional section, we could really think of it as being like a, we can think about it as being like a PD controller followed by a low-pass filter. So it's like this. It's K times S over Z plus 1. So if I draw them in boxes, followed by this guy, 1 over S over P plus 1. So it's like PD control. And this is like a low-pass filter. Turns out that the cutoff frequency is P radians per second. Okay, so we can choose this pole to act like a low-pass filter. And this is also advantageous because differentiation is a noisy operation. So if you take a noisy signal and you take its derivative, if it's got little spikes and things, every time you take a derivative of the spike, you get like an infinite value. And so PD, the differentiation operation is very noisy. And so a phase lead controller, not only is it realizable, but it also, you can use this low-pass filter to sort of reduce the noise that's coming out of the phase lead compensator. So let's do that same example. Maybe I have enough time. I'll probably have to do another segment of the video to do this. I'm going to repeat the same example that I just did, but I'm going to show how we do it with a phase lead compensator. And I'm going to finish this video now, and then I'll start that in the next one. Okay?